Alright, this video accompanies the Unit 6 Similarity Radicals note sheet. So we've been talking about radicals and reviewing them from Algebra 1. So this was broken up into 4 sections to be able to help you refresh those skills. So the first example we're going to work with is making sure that we can simplify. And the easiest way to do this is to look for the factors of the radicand that are actually perfect squares. And it'll make life a lot easier as we go along. So when we look at number 1 here, we're given the square root of 48. So this is a multiple of 4 being a perfect square. But even bigger than that, we have a root 16 times a root 3. So 16 and 3 are factors, and that would give us a 4 root 3. Okay, 169 is a perfect square, so that works out nicely. Root 60, again looking for perfect squares. A factor of 60 is 4. 4 is our perfect square. The square root of 4 is 2. We're left with 2 root 15. And 15 cannot be broken down any further than a 3 and a 5. And since a 3 and a 5 don't produce a couple, we can just leave it at 15. Next we have root 98. And if I divide 98 in half, I get my perfect square of 49. Then the square root of 49 is 7, so my answer is 7 root 2. And our last example for simplifying is root 216. And 216 is a multiple of 36. It's 36 times 6. 36 is a perfect square, so we're able to pull out a 6, and we're left with a 6. So just remember, as we're simplifying, we are looking for couples. And so when we look for our perfect squares, that's a couple that's already together. All right, when we add or subtract radicals, we need to have similar radicands, just like we would when we combine like terms with variables. So if we look at our first problem here, we do need to simplify all these, because when we look, 20 and 45 are not the same. But if we simplify, we get 2 root 5 plus a 3 root 5, which is a 5 root 5. In example 2, we have 3 plus 2 root 6 plus 3 root 6. The like terms we can add together are those with the radicands of 6. So our final answer is 3 plus 5 root 6. In our third example, we need to break down 28. So I'm going to show a little bit more of a step here so you can see. Root 28 breaks down into 2 root 7. And 88 breaks down to 2 root 22. And 112 breaks down into a 4 root 7. So the reason I showed this step here so that you recognize that the coefficient has to be multiplied by the number that we're pulling out of the radical. So we have a 6 root 7 plus a 2 root 22 minus an 8 root 7. So our 2 root 22 is still by itself, but now we're subtracting a 2 root 7. Okay, the third area we're trying to recall and brush up on is multiplying. And when we multiply radicals, we have to multiply radicands with radicands and coefficients with coefficients. So if we look at our first example here, we have 2 times 4 is 8, 5 times 3 is 15. I cannot simplify 15, so I'm done. Next, I'm going to be multiplying a root 3 times a root 6, and rather than write root 18, I'm already thinking ahead, recognizing that root 6 is made up of a 2 times a 3. So I don't want to put them together, but rather I want to break the 6 down so that there's my couple. That 3, right, that pair needs to come out, giving me a 3 root 2. Next is our example with an exponent. The exponent has to be distributed to both the coefficient and the radical. So I have a 16 times 3, because remember the square root and a square undo each other. My final answer is 48. And the last part that we want to recognize is that it's called rationalizing the denominator. we can never have a denominator that contains a radical. Okay, so in order to do this, we know from the previous example when we worked with the exponents, if we multiply a radical by itself, we're left with simply the radicand. So that would be our objective right now. So always start by simplifying anything you can prior to just going off and rationalizing things. So my 6 cannot reduce with anything. However, my 10 and my root 2 can reduce, giving me a root 5 in the numerator. So my answer is 6 root 5, and I didn't even have to rationalize. If I look at my next example, so if we look at the next example, we are able to reduce not only the radicands, but also the coefficients. So we take our 12 and our 3, and we reduce them to be a 4, and we take our root 3 and our root 6, and we reduce those. Let me see if I can cover this back up because I don't want it to be confusing to see everything. So we take our root 3 and our root 6 and we reduce those. So we have a 4 over a root 2 because our square root of 1 in the numerator would just be 1. So now, in order to undo this root 2, we want to multiply it by itself. Because when I multiply it by itself, I'm going to get just a 2. So I can't change the problem when I do this process. So I have to multiply both the numerator and the denominator by a root 2. So as you've already seen, we have a 4 root 2 over a 2. Okay, so 4 times root 2 is 4 root 2. Root 2 times root 2 is just a 2, which is exactly the purpose of multiplying this root 2 by root 2. And now I can just simplify, and I have a 2 root 2.